But anyway, we got a great show. It's like a personal viewing for you guys, at least for the first, hopefully not much more than 20, 30 minutes, but welcome.
Okay, so my name is Dr. Garofalo. I teach in the biology department as well as science education, and this is the Hayden Show. So the Hayden Show has been around for quite a while. Even before we started doing Hayden shows, there's always been chemistry demonstrations that have happened in this room, going back quite a bit to the 1950s. The show is named after Dr. Thomas Hayden, who's director of laboratories. He was a teacher and a colleague, and this lecture hall has been named after him. The Hayden Show was named after Dr. Hayden by two professors that were here that started doing this demonstration annually. So you're going to see a lot of really cool chemistry demonstrations this morning. Good morning, everyone. As you come in, just fill in any empty seat that you see. There's going to be lots of lights, maybe some explosions. So if you want to take any pictures, any videos, definitely a good idea to do so. You're going to see a lot of cool experiments. This show takes a lot of work and an effort by a lot of people. You see everyone's names there. You're going to see them as they come out, but also the people that have been helping behind the scenes in just the prep room. So I just wanted you to all know that it's a big undertaking. It's a show you're going to enjoy. And really, without any further ado, I'm going to switch over to the camera so you can see either right live in front of you, or you can look up and enjoy the show. Thank you.
How you dressed it up? How you fucked it? Or is it just like
Do not stand up.
That's
Do
it?
not get off.
Alright, good morning, everybody.
No, I'm trying to lift it up.
We're
So I
going
can
to
see
start with a celebration off with a celebration.
Yeah, this is mine. Oh, like that.
Birthday today, by any chance? Jackie! Happy birthday, Jackie! That's exciting. Alright, so everyone, we're going to sing happy birthday to Jackie today. Alright. Happy birthday to you. Happy birthday to you. Happy birthday, dear Jackie. Happy birthday to you. Oh man, I had a surprise for you. I thought there would be something, but guess it might not be the happiest of birthdays for you. Maybe if we wish really, really hard, everyone. Let's see.
Are you doing it?
Can we make it an explosive birthday for Jackie?
It's not this, right? This? Oh, right here, I got it.
And then I was like, I feel like they won't. No. Right the second.
Those of you coming in, just find a seat quietly. The show is currently ongoing. Thank you.
Okay, so does anyone know what dry ice is made of? So, right, got dry ice here. Yeah.
Water.
Nope. Nitrogen. Carbon dioxide. Right. Does anyone know what a fire extinguisher is made out of? Someone stole my magnesium, but so what I'm going to show you here today is I'm going to make a really big fire with the stuff that a fire extinguisher is actually made of. So here I have some magnesium turnings in the dry ice. And after Jackie's birthday, we have Valentine's Day coming up, right? So I like to call this one the hunk of burning love. Because even the power of a fire extinguisher, carbon dioxide, is not enough to extinguish magnesium's love.
call me magician, Bond the magician, okay? So, you know why? Because I tend to make drinks for everybody. Somebody comes to my lab and say like, I want water. No, I can't have water. Just start by making something very interesting. Still water. Can you make something nicer? Ooh. That's for good for only one person. Let's make it for my entire lab, guys. This is for you. I think they can hear me without any mic. Alright. So you know what? Don't like it, want to go back, rather have water, it's much better. So let's see if we can convert it back to plain water. Very good, guys. We got water for everybody. Maybe you want something healthy? Water is pretty healthy. What is healthy? What's something better than water? What do you like?
Chocolate milk.
Chocolate milk. No, plain milk is better. That too, skim milk is far better. Right? Alright, let's do the skim milk for everybody. Milk without any lactose. So the lactose-free milk. You said chocolate milk?
Yeah,
I'm going to make it easy for you.
You make me chocolate milk?
Yeah, let's see if we can make it.
That looks rich and thick.
Just a thick chocolate milk. Alright, perfect. But if I don't like the chocolate milk, I can always go back to water and make it thick. Alright. Your chocolate milk is gone now. Alright. This is called the soda series. We have it all on the paper to see how it works. Enjoy the rest of the show. I'll be back.
One of my professors when I used to be a student here at Queens College. I now teach in Townsend, Paris. My name is Mr. Heitman. Some of you might know me. Few things we have some rules about the show. If you see something really cool, you say, ooh. Say, here, let me hear you say it. Ooh. Alright? If it's very interesting, you might even say, ah. Say, ah. And of course, when there's something like really, really cool, you go, oh yeah, oh yeah. Let me hear you say that one. Oh yeah. Oh, I got it. All right, that's good. How many of you ever heard of the Hindenburg? How many of you heard of the Hindenburg? You've heard of the Hindenburg? What do you know about the Hindenburg? It exploded. Do you know why it exploded? It did. It used hydrogen. I love to demonstrate the Hindenburg right in front of all of you because the dirigible Hindenburg was flying around New Jersey and went just like that. That's right, just like that. And I thought that's pretty cool. And that's why they don't use hydrogen in dirigibles. It's very, very dangerous. Very, very dangerous. Thank you very much, ladies and gentlemen.
There's a person celebrating a happy birthday. Do you want to do it? Yes! Hey!
gonna startle knowing it's gonna happen. I'm gonna jump.
You think we should?
I don't have. No. No. Don't do it.
You guys have insurance? Life insurance. Even though Candle doesn't want to do it. Mommy, please. What you really witnessed was the difference between hydrogen and helium. Both less dense than air. However, one a little bit more flammable than the other, I would say. Thank you very much, ladies and gentlemen.
Alright, I need matchsticks. Just like you, I'm gonna blow up something. But alright. So all of you heard about combustion reactions, right? Combustion reactions. Okay. I got the same hydrogen, but I don't have any helium. Okay. So let's see how the hydrogen trapped in these soap bubbles, is it going to explode like that balloon? So I'm going to put them up here. So this is bubbles which has trapped. Was it as exciting as it was before? Joel, you stole my show. Maybe I'll try something better. Okay. This one has got something other than hydrogen. It also has got oxygen put in there. Okay, everybody knows water, right? Water is made up of 2 parts hydrogen and 1 part oxygen. So I got that in the bubbles trapped here. So let's see how that behaves. My hands are wet, so I'm told that I must light this matchstick in only 1 strike. That is called a Dynamite Soap. 2 parts hydrogen, 1 part oxygen make a perfect stoichiometric ratio. The effects are very different. Thank you.
Dissociates. Good. All right, so now I'm starting to see some electricity. I'm starting to see that the water is conducting electricity. And as I add more salt, I'm adding more and more electricity, right? It's able to conduct more and more electricity. So I also have Gatorade here, and what's Gatorade's big marketing thing?
Electrolytes.
Electrolytes, good. All right, so let's see Gatorade's electrolytes in action. Not as good as we thought it was, huh? So the thing is, Gatorade is actually a lot more sugar than it is electrolytes, right? So I'm not recommending that you drink a bunch of salty water if you've been outside playing basketball all day, but maybe look for some more effective alternatives to your electrolytes. Thank you.
Hello, ladies and gentlemen. I have a little container here. Didn't want to spill it. I thought rubber gloves were kind of cool. But I like danger. Danger's good. So I have some money. I have some money. You got some money? Oh, you want? No, I'm looking for someone to give me money. You want to give me some money? It's your birthday. It should be birthday money. Huh. I like how she thinks. Ask mom and dad. Maybe they can help you out there. Grandma, grandpa. I'm sorry. So, do you have any money?
I do.
Can I use it for my demonstration?
Can I trust you, Mr. Heitman?
Can he trust me? Yes, you can.
Oh, okay. I can?
Yes.
What do you think?
No.
No. But I'm feeling kind of generous today.
I appreciate it. I appreciate it.
Feel a little too generous. Is this enough money?
Oh, that's plenty. That's plenty. That's plenty. Oh, very nice.
I'm gonna get that back, right?
Oh no, I just put it in some alcohol. Oh.
Yeah. Oh, good job.
Burn it?
Burn it.
Okay.
What?
There's a boat fire.
That's good. There's a fire.
Oh, look, the fire.
Why didn't it do that? So, what's great about the American currency is it's not really paper. It's cotton. And the cotton absorbs liquid. And that was a solution of alcohol and water. But the water gets absorbed into the cotton before the alcohol does. The alcohol stays on the surface, and the water protects the money from ever burning. Thank you very much, Dr. Jalal. Oh, look, gummy bears. What we have here is something called potassium chlorate. Potassium chlorate is a really great thing because it has oxygen in it, an extra oxygen, and it's in a solid form. But when we take that potassium chlorate and we heat it, we create a liquid out of it, and that liquid has enough oxygen in it to help with the next thing that's about ready to occur. Come on, be careful, I don't want to break your glass. It should. No, can't reach.
Everything's fun today.
Oh, can't reach. It's okay, it'll still work. This is a gummy bear. This is my friend Pete. Everybody say hi, Pete. Hi, Pete. say, Pete, in the name of science, would you be willing to go into our solution down here? What do you think Pete says?
Yeah.
Of course Pete says yes. Why? Because Pete is a good gummy bear. Pete understands that we do things in the name of science all the time. Everybody say bye, Pete.
Are we allowed to do that?
Smells like cotton candy, doesn't it? What's a gummy bear made up of? Sugar. Sugar reacts with oxygen and will immediately combust. Pretty cool, isn't it? That's Pete's little brother. Thank you very much. Gummy bear sacrifice.
Olga and Rebecca here, and we are going to show you some different aspects of science and nano-learning. We're going to start a specific reaction. That takes time, and we call it the lazy reaction. We're going to start with solution A, that's a secret solution. And solution B, and both of them note that they are colorless. Now in a minute we're going to put them all together, and like I said, this is the lazy solution, so we're going to count together how long it takes for the reaction to actually happen. So let's start counting as solution pours it in. Okay, help me out. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Now there is another aspect of a reaction, which is something we call an intermediate. So an intermediate is a byproduct that we form when a certain reaction happens. So I'm going to start with solution A, solution B, and solution C. Now to make this reaction happen, we first have to mix these two, and mix these two. Now don't stop watching even after you see the first change. Yeah, that one is not that lazy, but we can start counting. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I guess it fell asleep in the way. Didn't happen. We did test this. It did work before. Yeah.
Boom!
Sorry, guys. We tried. You know what? I think I know why. I don't know if I can fix it. There's another beat. Okay. So, yeah, that's fine.
Wrong
Okay.
beat.
That's the wrong beat.
Wrong
But
beat.
that's okay. We have something more excited for you. Because we're going to learn about the Firefly chemistry. Chemistry of a firefly. What do you know about a firefly?
It glows.
It glows, right? 1 second, guys. Alright, so let's talk about the Firefly. We know that it does what? Glows in the dark. And did you know that the reason it glows is because it has a special chemical in there that makes it glow? It's not real powder. Sorry guys, we're missing an essential ingredient for this to happen. Joel, you want to start with yours and then I'll
Sure, no problem. I got your back.
Thank you.
How many like the 4th of July? Why do you like the 4th of July? Fireworks, right? Fireworks make everything so cool. I'm pretty boring on fireworks though. And because I'm a chemist, and so it kind of started out that way, because I had a really good mentor who really took, well, the fun of fireworks away. Because they taught me in chemistry that fireworks are nothing more than salts. Metal salts, like calcium chloride, strontium chloride, barium chloride, some other chloride, cupric chloride, sodium chloride, no chloride, just boric acid. And see, we got fireworks. What we really learned was that if we took these salts and we excited their electrons somehow, that when we excited those electrons, we would see a change in energy, because the electron would go up in energy level and then would come down. It would give us pretty colors. So I give you the activation energy of methanol and the salt of fireworks and the pretty colors that they will make. Lights, please.
Stand up for a second to see the colors.
Feel free to stand. Barium makes boric acid makes this beautiful green. I feel like I'm in Harry Potter. We have some other beautiful colors moving on there.
Add ammonium hydroxide. What happens if I add ammonium hydroxide? What color is it going to go? Any guess? We go back to our green color. So we said ammonia is the base, so we have our green color back, guys. All right.
There's a bag. I thought it was a front.
We got the beer. There
I said I believe it was a bag. I thought that was it. Yeah, I was like, look, I admit this.
Yo.
No, you didn't.
Whenever the next explosion happens, I just yell at the
Don't do that. Don't do that. Don't do that. What's up? I don't know. Something funny. Oh, no, he's just gonna yell outside down. I don't know. So he's gonna yell something.
Don't do that, bro. Empty. Don't do that.
Are you sitting? I mean, I'm not like a real person. I'm not actually. South American.
What? He's got vacation.
But I'm not like.
We're all stimming.
I'm like that type of person.
Hello everyone, good morning. Here I want to talk to you about superconductors, okay? Superconductors are a unique material that basically have zero electrical resistance and expel all magnetic fields when they're at a critical temperature that is extremely low. What we're going to be using here is liquid nitrogen. That's going to bring it down to about negative 200 degrees Celsius or around 70 degrees Kelvin. Now what happens here is that when the magnetic field is expelled, it produces something called the Meissner effect. And when we put it in the presence of these neodymium magnets, which are rare earth minerals, they're going to do something very unique. So you'll see right here. I take this, put it right on top. There you go. It's levitating right above the magnet. And this is not a trick here. See, it's legitimately levitating on top. This occurs because this specifically is a YBCO type of superconductor, type 2, which means that it's got little holes in it that allow the magnetic field to go through it and cause it to pin itself in place, magnetically levitating throughout the entire thing. And I'm sure all of you have taken the MTA before and always wondered, I wish this thing would go faster. This isn't just some, sci-fi principle that's used in movies. This is something that's actually used today. In fact, it's used in Japan and in Korea and in China for maglev trains. It's the principle behind the maglev system. And if you see right here, you can see that the quantum pinning effect does keep it in place, just like it would keep that train system in place, as long as it has some sort of push. It can, in fact, be used as a way to transport people. And in fact, it doesn't just transport people at the same speed as a regular trains. Regular trains here in America, especially the ones that go interstate, go about 125, 150 miles per hour, which is pretty good. But maglev can go about 300 miles per hour on average. In fact, the fastest train ever reported in existence was a Japanese L0 series that went about 370 miles per hour. Now you can see here, if I take this magnet, with the quantum pinning effect, you'll see that it floats in place. It actually spins there. You can zoom in on that. Whew. That's so cool. This is something that's actually used today. Upside down? Oh, sure, yeah. I'm going to change that. This is one of the cool things. This isn't just regular magnetics, repelling and attracting each other. This is actually levitation. The magnet is actually holding the superconductor in place here. And I can actually spin it upside down. See that? This is used today in something like an MRI machine. I'm sure all of you are too young to have an MRI, but your teachers are well equipped and knowledgeable about those caskets.
Can they do it for the roller coaster? Can they go upside down and rotating?
Maybe in the future, we don't know. In fact, maybe in the future someone can use this to create an engine. Some theoretical estimates have this going in circles in, say, sub-zero in 0 degrees Kelvin for about 100,000 years, maybe even longer than the heat death of the universe. Currently, though, realistic estimates have it about 26 years, which is still pretty amazing. This thing has to be kept consistently cold in the liquid nitrogen, so I keep it in the liquid nitrogen bath to make sure that it stays at around 70 degrees Kelvin. In fact, this specific superconductor is a high temperature one. The previous ones would go at close to 4 degrees Kelvin, which is close to almost absolute zero. And that would only be possible with something like liquid helium. So actually the technology is getting better and better by the day. today in America, there are 2 systems that are being created that will hopefully produce maglevs, so that one day we can easily travel from New York to California without taking an expensive airline in about 8 hours. That's about 2,900 miles in about 8 hours, which is the plane takes about 6 hours, which is pretty impressive, especially considering how many people that the train can take. So you can see here, just with a little bit of propulsion, the system that sort of takes place there. Anyways, that's been magnetic levitation, that's superconductors. Thank you all for
Alright, so New Year's just passed, and one of my New Year's resolutions is to start going back to the gym, but I haven't really gotten into it yet, but I like to think that I'm pretty strong, right? So, who thinks I can crush this can? I can crush this bottle, squish it that way.
I can give it to somebody here.
You guys don't have any faith in me, huh?
No, we don't.
Here, check it out. See if you think I'd be able to
Your
crush
bare
it.
hands straight out. Come on. You try. Maybe. Maybe I'll give it to Victoria. She can do it.
Well, I don't know. I'm pretty confident. I feel like I'd be able to crush it, but I'm gonna use chemistry. Okay, I'm gonna cheat a little. I'm gonna use chemistry. So we had the bottle rocket over there, right? So I'm going to take some rubbing alcohol here, and what I'm going to do is I'm going to turn it into a gas. And what do we need to use to turn a gas into a liquid? Heat, right? We need some energy to turn it from a gas into a liquid. So, see, I'm using my muscles. I'm getting a little bit of a workout, okay? Alright. So now I'm going to dump the liquid part out.
Mythbusters and Thermite, they cut the car in half, right, with Thermite. Well, somebody tried to do something similar here a long time ago with Thermite, and, well, they went through the pan. Thermite heats up to an extremely high temperature, over 3,700 degrees. They've used it in rockets, like NASA likes it in rockets, because once you start the reaction, you can't stop it. It only stops when it's done. Right. Oh.
The friend being.
This is the fuse.
Run away if you...
The thermite will come out the bottom in a stream. That's the thermite.
But I am melting all over this place.
Yeah, I like that. And I've just made iron here, right here in Queens College, and it's really, really, really hot. And sometimes, ooh, I just melted it to the tongs. Pretty cool. I've never done that before. That's a new one. I like that. Sometimes you see them use thermite on the railroad. They actually weld the tracks together using thermite. Pretty cool stuff. Thank you very much. That's thermite reaction.
Okay, so at my school, I don't know about your school, but we're not allowed to have any gas on, so we can't use Bunsen burners, and that means I can't use any fire, which was like one of my favorite things. So it's a little sad for me. Where's you guys from? And I'm going to show you guys one of the reasons they probably don't let me personally have any fire going on. Yeah, I do need to go to the gym, huh? Alright, so what I have here is soapy water. So the bubbles that you see here are filled with very flammable gas. Alright, so I think that is enough fire, enough flammable bubbles.
Ready? Go. I've always wondered what a diaper's made of. I really have. I have a diaper right here. I have some water right here. I have to believe. Have some food color right here. Realistic effects. Ah, yes, I feel it now. Kind of looks real, right? Well, we take this and we put it into the diaper. It's amazing how much a diaper actually holds.
favorite 3D actor. What?
Good to the last drop. It's really made of something called sodium polyacrylate, and it is a chemical that when given the opportunity, taking a little itty bitty bit and filling it with water at an extremely rapid rate, will absorb all the liquid inside of it. That's pretty cool, right? Sometimes, when you realize you see a professor of yours in the audience who gave you a bad grade, you might want to come over to the professor. Oh no, I was given a bad grade. Do you think I should turn it upside down? How many people say yes? How many people say no? Not enough. Ready? 1, 2. Oh no, it's ripping.
Supposed to trust the science. It's crazy. It is crazy. I don't know.
The science broke today. Oh, it's okay. That's a lot of absorbancy from such a little bit of powder. Ladies and gentlemen, sodium polyacrylate. Oh, my favorite.
Alright, so, what do you guys know about Mentos and Coke? It explodes. So we've had a couple of good fire explosions, and now that we're getting close to the end of the show, we're going to do a little bit of a sugary explosion. So I like to bring my umbrella for this one. Alright, you guys ready?
Oh, please, what do you get? Aeroplane umbrella?
It's for Jackie's birthday. I'm so excited that it's your birthday. We usually don't have someone here with an actual birthday gift. Alright, are you guys ready? It's gonna get wet and sticky here. And count me down.
3, 2, 1.
It's a small one. I didn't think I would ever.
I think we've come to the end of our show. But before you leave, I'd like to give you a demonstration of something called calcium carbide. Now, calcium carbide was used by the miners when they were in coal mines, mining coal. And basically what calcium carbide is composed of is limestone. And when the calcium and carbide, the limestone, when the calcium carbide is wet, it releases something called acetylene. And the acetylene will provide light. They use these things called the lamps on their head, and that's what they used in the mines. But then that transferred to the stage in Broadville, something called, Broadville. Some of you may have heard of that in a book. Yes, we do read still, right? Books. But it was the term transferred to being on the stage called being in the limelight. And that's true. It came from calcium carbide. And so what we do is we add a little water to this, and it releases the acetylene gas. And well, like everything I do, can I get a lighter? Lighter. Everything I do, there's always like a really good. Oh no, absolutely not.
What about the Big Macs?
Sure, you like that for me. So I'm going to put a little bit of water in here. I'm going to hope I don't go deaf because it's been a while since I've done this.
Oh.
You like that? I'm going to aim it. Who am I aiming for? Yep, right there.
That's so nice. Oh.
3, 2, 1.
time here at Queens College. We hope to see you again soon. This is the fun that you can have for chemistry here when you're undergraduate degree. So thank you, everyone. Good to see you. Enjoy the rest of your day. Welcome to the Hayden Lecture Hall. Before we begin, we would like to introduce you to the college, and we have our Queens College president here, Dr. Frank Wu.
Good afternoon. How is everyone? All right, are you excited to see some stuff blow up? I come every year for this show. Welcome to the beautiful campus of Queens College. I'll be very brief. So this chemistry demonstration is named for Chief College Laboratory Technician Thomas J. Hayden. That's who the room is named for as well. And it's put on by the Department of Chemistry and Biochemistry today. This is the 27th time that we've put on this annual show. So it is a long-standing tradition of this great institution. You know, science is just fascinating. It is so important to everything we do every single day, and chemistry in particular. I know that here at Queens College, our talented faculty and the lab technicians teach it in a way that it's meaningful, it's exciting, it will captivate you. This is just a tiny little bit of what goes on in the laboratories here at Queens College. We want you to have some sense of it. I'd like to commend and thank everyone involved for putting on this show. That includes, in particular, the Science and Education Division alumni who support the Finkenberg-Gaffney Scholarship in Chemistry. There are actually scholarships that you can get to come here to study chemistry in particular. Do we have any Queens College alumni in the room? I know that at least one of the presenters is a Queens College graduate. So raise your hand if you're a Queens College alumnus. All right, thank you so much. So, I want to be sure to welcome all of you high school students. Our School of Math and Natural Science is the perfect place for you here in New York City, in the world's borough, to study chemistry or any other scientific field or math. It's a great place to earn your bachelor's degree or even to come on the accelerated track and earn a bachelor's and a master's in the amount of time that at most places, and the cost that at most places, will only get you a bachelor's. So think about that, and you can get all sorts of hands-on experience here, and that includes so many other fields as well. I'll just mention a few. Astronomy, geology, nanotechnology, computer science, neuroscience, and biotech. There's just no limit to your options with a math or natural science degree here from Queens College. One of our recent graduates went on to an internship with NASA, and that showed that even the sky isn't a limit if you're here at this wonderful institution. I'm honored to welcome you, and I know that we're all here to see the stuff explode, so I'll stop talking, and it's just a great show, I promise you. We hope to see you when you graduate from high school right back here, and maybe someday you'll be one of the ones in front of the audience destroying things. All right? Thanks so much. Back to you.
Thank you, President Wu. So this is the 27th annual Hayden Show, and as President Wu mentioned, it was named after Professor Hayden, who has been doing demonstrations in front of his chemistry classes and camps and other events just like this since he started in 1955. As I mentioned before, the lecture hall that you're sitting in is named after Professor Hayden. And 27 years ago, the Hayden Show, where we get to see things explode, started with Dr. Streckes and Dr. Gaffney, and we continue it today in Dr. Hayden's honor. Here are just some of the names of all of the people who have put the show together. You're going to see many of them behind the lab bench, but there are many more in the stock room. So we're looking forward to a really great show. There are going to be times where you may want to have your phones out to take pictures and videos. There's a lot of cool experiments coming. So I'll hand over to presenters. Enjoy the show.
So, there we go. All right, do we have any birthdays in the house today? No? Anyone's birthday, like recently or maybe coming up? Tomorrow. Oh, tomorrow. What's your name?
Billy.
Billy. All right, so we're going to start Billy's birthday a little bit early, and I have a birthday candle here that I'm going to light for him. All right? And we're going to sing Happy Birthday, all right? You ready? Happy birthday to you. Happy birthday to you. Happy birthday, dear Billy. Happy birthday to you. All right, make sure you make your wish. Oh, I don't know, Billy. It looks like your wish might not come true this year. Let's see. Everyone cross their fingers for Billy. I guess it didn't work.
So, can they get the birthday cake?
Carbon dioxide, good, right? So, it would be reasonable if we would say like dry ice would put out a fire, right? Yeah, that makes sense. And next month we have Valentine's Day showing up, so I'm going to show you one of the greatest loves of all time, the love between magnesium and oxygen. So, for magnesium and oxygen, their burning love can't even be put out by the fire extinguishing properties of carbon dioxide. So let's see. Lights. Burning love, I call it. Thank you very much.
You know what is that?
Maybe I need a mic. Alright, so here I'm here to make some cool drinks for you. Usually water is very nice, so this is some nice water. Cool. Maybe something very interesting for you guys would be to have nice colored drink, right? So when you see some color, see, ooh. Let's see if we can get some color. Here we go. And let's make it for everyone. At least everyone can get a drop. I guess there's a big audience here. But if you want to get back to water again, we have again chemicals for that too. We can make the water and make the color disappear just like that. Magical. Whole thing is gone. Maybe you want something nice, cool, healthy. Healthy, what do you want? Milky. I have milk for you. But skim milk. No lactose. There you go. My skim milk. So let's just make it for all. Skim milk for everyone. Maybe I think it's like one thing I have no milk. Maybe it's something like chocolate milk. I have chocolate milk for you. Just for you. There you go. Chocolate milk for you. And maybe somebody likes no chocolate milk. I would rather have water pack. Yeah, you want water? Okay, I'll make water for you. This is water for you. Right, there is this chocolate milk turning into water. Don't drink it! It's like not even drinking it. Alright, the whole thing is made into water. I can just pour it a few times, everything becomes water. Clean water. Now it is chemically purified. Right, this is called the soda series. You want to know the chemistry behind this? There is a paper in front of you. You can read that. That tells you how the chemistry works. Thank you.
All over the place, we have these things called dirigibles. You know what a dirigible is? It's a blimp. Fancy name for a blimp. You know what was in a dirigible? Hydrogen. They put hydrogen in a dirigible. And there was this thing called the Hindenburg, and it was in New Jersey. And it was flying over New Jersey when suddenly, for whatever reason, unbeknownst to anyone aboard, it caught on fire. And it crashed, but it was filled with hydrogen. If you want to go on that go, right? There it goes, hydrogen. Is your insurance paid up? Insurance. Health insurance, life insurance. Can you come to this one? Did you saw the last explosion? No. No, I'll do it. It's okay.
What is the Hasan?
Ladies and gentlemen, what you just witnessed is the difference between hydrogen and helium. Both gases less dense than air, but hydrogen extremely flammable. Helium, not so much. Thank you very much.
Alright, I'm back. So here I'm going to do something, the same hydrogen gas, but I got it trapped in a bottle here. So I want to see if these bubbles are going to be as explosive as his balloon is. Maybe? What do you think here?
They're just little tiny bubbles, though.
They're tiny bubbles?
Yeah.
Not be as good? Okay. She's right. She knows more chemistry than me anyway. So I'm going to put those bubbles in here. Okay. Let's see if these bubbles are any good. that one doesn't like. Yeah. Funny. Okay, so here is something else. This one is called as the stoichiometric mixture, the right ratio, the mixture of the hydrogen and the oxygen put together. Does anybody know what's the ratio between H2 and the O2 in water? 2:1, okay. 2:1 ratio is already pre-mixed, but it is in the form of a gas. It's going to try to form water when I'm lined up. So let us see whether it will fully combine or whether it's going to combine with any effect. Somebody is hoping for a thunder, I guess. Let's see if it has got an explosion like a thunder. This one is crazy. These matches are no good.
In it, and the oxygen is in a liquid form. And this is Sally, and this is Pete, and Pete and Sally go out, and Pete gets in the way of the hole for Sally because he doesn't want Sally to fall in the hole, and Pete falls in the hole. Say goodbye to Pete. This is the combustion of all the sugar inside a gummy bear. And it's just reacting with the oxygen that's inside the test tube. And it's quite interesting. And when all the sugar's gone, the reaction will stop. But does that mean all the oxygen's gone? No. Well, that's a good answer. Because we'll just throw Sally in for good measure. Wait for it. Wait for it. Uh-oh. There we go. And that is what we call the gummy bear sacrifice. Thank you very much. I lost my wallet. I need some money. Does anybody have any money? You have some money? How much you got? You got 20? No, I need more than a 20. I got 50. What do you got? 30. I need more than 30. I need a big bill. Who's got a big bill? You got 100? Let me see it. Hook me up.
I think you dropped it. I think I found it down.
Oh, look at that. Oh, look at that team dropped you 100. Oh. How do I know this is yours?
Because you know, it was mine. So
It's yours?
Yeah.
Right. It's definitely 100. What am I doing? Well, it's not my money. I don't care about the money. I want to put it in some really good stuff. We call it alcohol. Stuck it together. Let's get it back in there one more time. Really pull it down there really good. Yeah, there we go. That's good. Thank you, Dr. Galafalo. I just found it. Money.
What? It's okay.
So money is a very interesting thing we have in the United States, especially our money, because, you know, we call it paper money, but it's not really paper, it's really cotton linen. And the linen, actually, the cotton has a very unique property where it absorbs certain liquids. And I had a small mixture here. It was alcohol, but it also had water in it. The cotton fibers actually absorbed the water before the alcohol, even though they're mixed together. And the alcohol stays on the outside. Meanwhile, the water absorbed into the cotton fibers, protected the money, and kept it brand new for me to take. Thank you, Dr. Jalal. Follow. Have a great day.
You guys having fun yet? Yeah. Okay. We're gonna get to some other type of science, which is showing you different types of. Okay. Wrong place. Okay. Now you guys can hear me? Yeah. Awesome. So we're gonna show you a reaction that, as we call in chemistry, the lazy reaction. It doesn't want to do anything. So, we have solution B, I started backwards, but it's okay, mixed with another solution A. And when we mix them together, they're supposed to react, but this reaction takes a little bit of time, so you're going to help me out. Let's start counting. 0, 1, 2, 3, 4, 5, 6, 7, 8. Oh! That is great. Now we're going to have another one. This one is a little bit different because in this reaction, we form something that we call an intermediate. An intermediate is a product that you get before you actually get the real product. So we're going to mix 3 different solutions. Solution A, we have solution B, and we have solution C. And when we mix them in specific orders, they produce a product that is not the final product, but then, in a glimpse of a second, produces the third. So keep watching, and if we can have the lights off. Now the next thing we'll do, you can turn the lights on for now. The next thing we can do is study the science of a firefly. What's a firefly, guys? It's a fly with some light, right? Have you ever seen a firefly at night? What happens? It glows, right? So that glow is an actual chemical. It's a chemical that we have right here, and we're going to make that magic in a bottle. So when we mix that, if I can have the lights off, please. Yeah, the firefly in a bottle. Thank you guys, enjoy the show.
Such as calcium chloride, lithium chloride, barium chloride, strontium chloride, follow the mountain below. Cupric chloride, yes, there we go, we're learning. Chemistry is definitely contagious. sodium chloride. Yep, there we go. Sodium chloride and boric. No, boric acid. Got that one wrong. And so those are these wonderful salts that we have. And then what we do when we have fireworks is we give it some type of activation energy to make the electron go to a higher, well, energy state. Goes up in an electron shell, and it becomes what we call the excited electron. But we still don't see color yet. We only see color from that electron that is in that excited state when it wants to come back out of the excited state. So the first thing we do when we make fireworks is we have to excite that electron through different colored salts. And so we will now excite the salts. Give it some seconds. We gotta make those colors come out. We couldn't. All the lights lit quick. Oh, that's pretty, right? I think those are incredible.
Now do they remember which ones are which?
That's a good question. I don't think I remember. Oh wait, lithium, strontium, barium, potassium, cupric, sodium, and boric acid. Alright. Yeah, boric acid's nice, I like it. You know, gives me an idea. We should make fireworks right here in Remsen Hall. Does it have? Yeah, right? Oh, what a great idea. I'm glad you thought of it. And the very first thing we need to do is we need to take that same chemical that I poured into that liquid and make what I like to call a propellant out of it. So if we can make the cap come off of this through a small spark, I guess we can't do it. There you go. I can give you the fuel. Give me fuel. Yeah. There you go. 1 drop, he says. I've been taught well. 1 drop. That's what you need. 1 drop. Nope, not working. Oh, it does work. Oh, so now we take the big bottle.
Can you see the colors now? It's coming up so nicely.
It is nice.
For 1 second, turn it off. Alright, you guys can see the color now much better. Those who cannot see, stand up and see right now, one more time before you put them out. Oh, the intense, there are 2 red colors. Crimson red and orange red.
Those are pretty. Your job is to see what color I put in here. Can you do it? Yeah. You sure? I don't know. I don't even know whether this is going to work or not. 3, 2, 1. I tried. Maybe later. Color fireworks. Thank you very much, everybody.
Okay, guys. How many of you here heard of acids and bases? Anybody? Yes. Do you have to have any acids and bases at home? Okay, great. So, how do we know if something's an acid or a base? How do we know? Okay, we gas pH meter. We don't want to test it ever though, right? Right? We know acids are sour and bases are bitter, but we have a unique method called the universal method to determine whether something's an acid or a base. Alright? So I have here some water, and my partner's going to pour some ammonia in it. What is ammonia? Acid, base? Anybody?
What's the base?
Okay, go ahead and pour it in. So I'm going to go ahead and add my universal indicator. Does anybody know what color this is going to change? Purple. Purple? I heard purple. Purple is a good choice. Turns a nice purple color. All right, so that means bases are purple, right? Ammonia is the base. So what happens if I add this stuff? What's this called? Dry ice. Anybody know it's an acid or a base?
Acid.
Dry ice, CO2, right? So it's neither an acid nor a base, but when we put it in water, it forms carbonic acid, which is an acid. So you can see it's going through, it's neutralizing the ammonia. It's turning blue, right, for neutral, then it turns to green. And if we keep adding it, we'll continue to see a color to acidic. Okay, so we started out purple. And anybody know what HCl is? Is it an acid or a base? Let's find out. Let's find out. Let's add some HCl. Ooh. So we got a different color here. This is red, so this is acidic. HCl is a very strong acid. Can we turn it back, do you think? I got some ammonia here. What color would it turn back? Purple? Let's see. Woo! Green. There goes green. Almost. Green. You want to stay on green? It doesn't want to change. Let's see. Get it back. We're getting there. Yay! I think we're there. Yeah, you can see the purple, right, guys? Yay! Turn it right back. Okay, there we go, guys. Universal indicator. Thank you.
Hello, I'm back again. Banana. Flowers. Oh, so pretty flowers. Pretty flowers. Keeping coldness. I love it. I love me some cold. What I have here is called a doer. And this is filled with something called liquid nitrogen. Bouncy. Banana. Yep, definitely a banana. Balloon. What's in the balloon? Yeah, I'm filled with helium. What's in the balloon? What do we breathe? From where? Oh, air. Yes, air is in there. Yes, I agree. You don't have any helium? No. That's why I'm so round to the ground. So, got the other doer? Yep. This is a bigger doer. I love it. And this is filled with liquid nitrogen. Very, very cold. Very cold. And so I'm going to pour the liquid nitrogen on the balloon. And what's happening to the balloon? What's happening to the air inside of it? Ooh. Ah. I'm melting! I'll get you, my pretty! That's cool. I can pack this up. Yeah, look at that. That's nice. I like it. The balloon is fluid. Look at this. It's fine. It's fine. I can do magic. Watch. Grow larger. Get bigger. Does that mean this is still a banana? So this is a cryogenic effect of liquid nitrogen. It makes things really, really cold. The balloon, it took all the air molecules and put them together and shrunk it. But for this, it doesn't bounce anymore. For the banana, there it is. There it goes. Up there it is. It's swimming. For the banana, it's so hard. I can take the banana and make a hammer out of it. And for flowers, I can dip my flowers into my liquid nitrogen, and I can freeze them, and I can take them out, and they'll still be flowers.
Yay!
But they'll be very crispy. There you go. Liquid nitrogen, ladies and gentlemen.
Superconductors are basically certain types of special materials that when you cool it down using what you just used right now, liquid nitrogen, to about -200°C, have unique properties which allow them to expel all the magnetic fields inside them. And that sounds a little technical, so I'm just going to show you what that actually means when you actually expel all those magnetic fields in what's known as the Meissner effect. You get something like this. There you go. A little bit of a levitation going on. Now you see, what's happening here is that when it's super, super cold, it creates this magnetic field that expels outward and creates this force keeping it upward. And this specifically is a type 2 superconductor, which means it lets little holes punch the magnetic field go right through it. What's really interesting is what happens when I put it on top of this. Because what I can do is, if I can see it against the screen, I can spin it around. I can spin it around super quickly. Get it? There you go. Yeah. And most of you are thinking, well, I've seen magnets before, right? I know how magnets work, right? That's not pretty cool, right? What about this? If I turn it upside down, I get this same sort of effect, and that's not something a magnet can do. So if I turn it upside down, you can see that it's actually floating in midair. And this is actually something that isn't just science fiction that we just use it in a laboratory and it just leaks it all. We use this in things called maglevs, which are magnetic levitation trains. They exist currently in places like Japan, China, and Korea, where they're used to move trains at speeds of up to 370 miles per hour, which is more than 2 to 3 times faster than what our normal trains go. So if you're ever wondering why isn't the MTA moving as fast as what they do in those Chinese and Japanese countries, because we haven't actually created these magnetic levitation trains yet. There are some that work right now in the Northeast from New York to Philadelphia, and one from Las Vegas to California. But you know what they say, when something's at work with the government, it's never really finished until someone's got his paycheck. Anyways, that's magnetic levitation, guys.
Are you having fun yet? Yeah! You like fire? Yeah! Of course you do. You should come to Queens College. You should be a chemistry major at Queens College, and I was. I got my master's degree here, and then I became a teacher, because I like to, well, make fire. Anyway, this is thermite. This is thermite. Thermite is composed of iron and aluminum. And when it's mixed together, who's seen, oh look, Thomas. Who has seen Mythbusters and they cut the car in half with thermite? You've seen that? Oh, one person in the back. It's pretty cool, isn't it? Thermite's really neat. They even use it in space. NASA likes to use it for rockets. It has some drawbacks. When you ignite the thermite, you can't stop it. And if you make a mistake with the thermite, which has been known to happen before, sometimes, just sometimes, you burn holes through things. Thermite burns at over 3,000 degrees. It is a one-way reaction. Once it starts, you can't stop it. And we're going to witness the thermite right in front of us, right here. And what we're going to see is I'm going to light this fuse with this torch. And when I do that, it's going to burn down and it's going to ignite the thermite. The thermite's going to take a second, but once it starts, you can see the thermite drop and drip right down through the middle. Are you ready? That's the fuse. That's the thermite. This is old thermite bonded with new thermite. This is new thermite. And then there's a piece in here still, an ingot. And if I do it just right, I can fuse it to my tongs. Ladies and gentlemen, thermite. Thank you very much.
Only my kids feel strong today. Alright, so I am going to cheat a little. I'm going to use chemistry to light it though. I mean to crush it. So what I have in here right now is rubbing alcohol. I put it in there as a liquid. Why do you think I'm shaking it? Who said that? To get it all around, but someone said, make it into a gas. Good, right? that's why.
Okay.
All right.
All right, ready?
Candy, guys, what happens when you eat too much candy? You get cavities, right? So we gotta make sure that she has her own toothpaste. But elephants got big teeth and even bigger tusks. How are we gonna make that much toothpaste? Well, I'm gonna tell you. One of the main ingredients in some toothpaste is hydrogen peroxide right here. So we're gonna add a little bit of hydrogen peroxide into this mixture, right? And then, what's toothpaste without the stripes, right? What colors do you guys like? I got which what do you want? What, red, blue, what do you got? Alright, got blue here, we're gonna add both. You know what? Let's go crazy, right? Let's add both. We got blue, we got red here, let's add a purple, you know? What the hell? Alright? And now we're gonna add a little squeeze of this detergent. And oh, it's kind of legit, right? But you know what? This reaction is just going very, very slowly. But what I can do is I can catalyze it to go even faster using this, potassium iodide. So if I add a little bit of potassium iodide, what happens is... Alright. Now look at all this thing that's all on the teeth.
Love setting stuff on fire. So when we go in the lab, we have these little things where gas would normally come out, and you can turn it, but nothing comes out. Probably because they don't trust students with fire, but at my school, they probably also don't trust me with fire because I would do some crazy stuff like this. So what I have in this, there we go. Alright, so what I have in this bucket here is just soap and Dawn dish soap. And coming out of this hose is the flammable gas that you guys saw make fire with the Bunsen burner here. So these bubbles here are chock full of nice flammable gas. And I want to make a lot of bubbles for what I'm about to do. Alright, so this is probably why they don't trust us with fire at my school. students have a hard time concentrating. And I thought that it was just like I was taking social media away from kids so they can't like text or whatever. But I found out recently that I'm also taking students' mirrors away from them. The other day I saw a student actually using their calculator as a mirror during class because they didn't have their cell phone to use. So what I'm going to do right now is I'm going to use chemistry to make a mirror. Being a little too rough with it.
You can do it slowly.
So let's see if I can make a mirror for my student
It's
who
about 1 minute time.
apparently the lip gloss was very important. We were supposed to be doing math, but she was using her calculator as a mirror instead.
It is for someone who wants to see now it's for someone. Can you see your face here? Right? That's how your mirrors at your home is made of. They actually put a... Oh, you're getting there.
Oh yeah, I can see myself. I can put lip gloss on now.
It just takes a minute to make a mirror.
It only takes a minute and some chemistry, which is why you should pay attention in chemistry class. And never put on lip gloss in the lab. Alright, so can you guys see yourself in it?
There you go, guys. That's mirror making.
I know you guys are probably enjoying the fire also. But what do we know about Mentos and Coke? Explodes. So we're going to have a different kind of explosion right now. I'm going to grab my umbrella just in case things get crazy. Alright. So... there we go. Alright. Step back, things are gonna get wet and sticky in here. You guys ready? Count me down. 3, 2, 1. There we go.
Chemistry here, and what I have here is what we like to call a carbide cannon. What comes out of cannons? I'm going to give you my socks today. I took them off just for you. But what's really interesting about the carbide cannon, it has something in it called calcium carbide. Calcium carbide, when it reacts with water, it creates acetylene gas. And acetylene can be a lot of fun. Even the coal miners used calcium carbide in their old school lamps. They used to wear them on their head. And then that went to something called vaudeville, where they put those lamps on front of the stage, and they coined the phrase, "in the limelight." The problem with the calcium carbide is, in a coal mine, is sometimes it builds up a little bit of pressure. And when it builds up a little bit of pressure inside that coal mine, crazy things like to happen. Alright, here we go. Water, cannon, calcium carbide. Mix.